Okay, so why do we do all this? Remember, we need to calculate lots of different likelihoods to sample as evenly as possible the space of models, and to calculate the denominator in the formula for the maximum posterior probability. So, to summarize what we said on Bayesian methods, they represent arguably the most elaborate way to infer phylogenies. They aim at maximizing the posterior probability of a model rather than its likelihood. So, in Bayesian terms, we talk about posterior probability, and that's the goal, the criterion to optimize. They are very computationally intensive, and sometimes jobs run for weeks on relatively large data sets. And I quote here, I cite some famous software for Bayesian inference of phylogenies. PAML does some Bayesian analysis, Mr. Bayes, PhyloBayes, and Beast is the most famous tool now. And you have the others of these softwares between brackets. So, final part in this course on molecular evolution and phylogenetics is about assessing confidence on the branches of a phylogeny. So, once we have determined that this tree is the best one, we have our best tree, we are very happy with it. We obtained it either within the framework of maximum parsimony, of maximum likelihood, or maximum posterior probability, Bayesian methods. At the end of the day, we want to know how robust the different branches are in that tree. We would like to get certainty or probability confidence, statistical confidence, in the different nodes composing this phylogeny. For instance, you want to know with what certainty can we say that the man is more evolutionary distant to the mouse than the mouse is to the rat, and this will be a high probability, of course. But let's see. So we have the specific best tree we got. It's a function of the alignment we fed the inference process with, and we can notice that if we were to have different sequence alignments on the same taxa, sequencing, for instance, different parts of the genome to get an alignment on which to build a tree, maybe they would lead to alternate trees, these different sequencings. So probably so, but maybe all of these trees would agree on certain parts of the tree, at least. Okay? So the idea of the bootstrapping procedure is to view the data that we have as only one of the subsets. The alignment we have is one subset of all the possible alignments that evolution would give on these taxa, okay? Or you could have sequenced at another moment, other part of the genomes, different individuals pertaining to the same species, etc., etc. So the idea is that to say, okay, if the alignment we are using is large enough, we can resample with replacement from the set of sites composing the input alignment, and infer the best tree corresponding to that resampling, and do that again and again and again iteratively. Okay, and then we compare the bootstrap trees we got with our original best tree, and we see if parts of the original best tree are found in a large proportion of all the trees we inferred, the bootstrap trees we inferred from our pseudo alignments, the alignments obtained by sampling with replacement from the set of sites. And the statistical support of a branch will be the proportion of bootstrap trees containing that split or that branch. So let's see graphically what this means, this bootstrapping procedure. And this illustration is also thanks to Joe Felsenstein. It's from his book Inferring Phylogenies, published in Sinauer and Associates 2004. So we have, at the beginning, forget about the bottom of this slide. At the beginning we have, or the framework we've explained so far is that we have sequences, so aligned sequences are made of columns of aligned characters that we call sites, and from this original alignment or from this set of sites we estimate the best tree. Okay? And this bootstrapping procedure is independent of the method chosen to estimate the tree. You can use maximum parsimony, maximum likelihood, Bayesian methods, whatever. So these sequences, this set of sites gives you this tree. And remember when we talked about maximum parsimony, I highlighted the fact that some sites are more in agreement with a certain tree, and some other sites are more in agreement with another tree. Okay, in maximum parsimony, you could see that a certain site has a parsimony score of 1 for a certain tree, and a parsimony score of 10 for another tree. So we would say that this site is more in accordance or gives its preference to this first to the first three of the two alternatives. So if we select a different makeup of sites because we sample the same number of sites as the original number here, but with replacement, so we take like twice this site. It's taken here, it's taken there, once this site, okay, and we make these 3 sites out of twice this site and once this site. It doesn't matter if you remember that we stick to the model of independent sites. It doesn't matter where you write them at the end. What matters is how many of each of the original sites do you sample, okay? But at the end we build what we call a pseudo alignment that has same length as the original alignment and that contains sites that are possibly repeated. This pseudo alignment on this one, we do exactly, we imagine it's a true alignment, and applying the same inference method as we used earlier, we infer another tree. And this tree can be the same, can be different than the original tree. Okay, we do this independently. We bootstrap several times independently. So I forget about the original, the first sampling of sites I made here. I forget completely. I make another sampling of sites. Maybe this site once, this site once, this site once. Okay, and I sample the same way the original alignment. And then from this new pseudo alignment, I infer, with the same method as earlier, an estimate of the best tree. So I infer what's my best tree, if this is my input alignment. So here now the premise that we have to compare these trees together, and more specifically, we have our best tree obtained on the original data, and we have a series of bootstrap estimates. And it's quite common to have 100 or 1000 bootstrap estimates. And ultimately, the last step that is highlighted in this slide is to say that we give as a support to a branch the proportion of bootstrap trees containing that the split. So if here we have the number of times we see, so let's say this is taxa A, and okay, the branches leading to a taxon, the external branches will always have a support of 1, because you will always find this branch leading to the final taxa A, you will find it somewhere here in any tree, okay? But if we consider this branch, for instance, this branch is the branch leading, if they are taxa A and B, connecting A and B to the rest of the tree, but A and B as a clade, okay? Maybe here you have A here and B here, okay? If A is here and B is there in this new tree, we say that the branch leading to AB doesn't exist here. So this doesn't give a positive count for the branch AB. Out of the 100 bootstrap estimates that we have, let's say we have 60 of them that have the branch leading AB, or 60 of them, in other terms, that have a cherry AB. Then we will say that we have 60% certainty of bootstrap support, to be more accurate, 60% bootstrap support for this clade AB. That's the bootstrapping procedure. So we associate a confidence value to each of the internal branches of the tree based on the number of bootstrap replicates that exhibit that specific branch. There are alternative statistical support schemes that have been developed, and I give 2 examples of such measures. We can change our viewpoint and say that a branch connecting on one side AB, and if you take this A and B as being subtrees, a branch linking subtrees AB to subtree CD is certain, or has a high confidence value associated with it, if the tree containing this branch has a much better likelihood than the trees obtained by NNI on that branch. So the trees being AC versus BD or AD versus BC. Okay, and if this is much better, if the likelihood of this tree is significantly better than this and that, in any case, you will be able to calculate a certain confidence value based on the ratio between this and this. Okay. Alternatively, you can also have the likelihood ratio between the phylogeny, including the branch, and the non-binary phylogeny that is not resolved on this specific node, that would be a phylogeny linking A, C, B, and D to one point, having a multifurcation there, or a branch of length 0. So we can calculate, still using the same kind of algorithm as Felsenstein pruning algorithm, using that algorithm, we can calculate perfectly well likelihoods associated with the tree containing multifurcations, right? So these 2 kind of examples or strategies use what we call likelihood ratios. The ratio between one likelihood and the likelihood of another tree, slightly modified, gives you a good local confidence value for the branch that is involved in the rearrangement. That's an alternative to classical bootstrap, and this alternative is much cheaper in terms of computation cost, because you know that calculating the likelihood of a tree is expensive, even if maybe in this case, I mean, we have to to do this inference process, to calculate the best the tree giving the best likelihood if we are in the framework of maximum likelihood. So roughly, if we use 100 bootstrap estimates, I have to calculate, I multiply my cost by 100. Okay, instead of having to calculate it once, I have to calculate it 101 to perform this inference process. While using likelihood ratios, in fact, you remember from Felsenstein pruning algorithm that local likelihoods are calculated in the process of calculating the likelihood of the whole tree. So calculating the likelihoods of these trees obtained by n and I is not expensive at all. Okay, so likelihood ratio branch supports or branch supports based on likelihood ratios are much cheaper to calculate than bootstrap classical parametric non-parametric bootstrap values. Okay, thank you for listening to me during this last session. It's been a pleasure to record these videos for you, and I hope you will enjoy your practical for this 4th day. Bye-bye.